Today we're going to be looking at the 2015 January Silver Contest problem cow routing. So for this question, Bessie is going to go on an airline to travel to various cities. She has N planes, each of which will basically go on a route, and each of these routes is going to go through a certain amount of cities. So Bessie's goal is to find the cheapest way to get from farm A to her destination of city B. So we want to give her the minimum cost and also the minimum amount of individual flights that she has to take to get this minimum cost. So the input is going to be read as such. We're going to have two numbers. This first number is going to be the cost of this entire route, meaning if I travel from here, from city 1 to city 3, it's going to be cost 3. And if I travel from city 1 to city 5 using this route, it's also going to be cost 3. So we're going to have the cost, the number of cities, then this route, and we're going to have N routes. The first number here is A, this is B, and we're going to have N. So the first thing we're going to notice is that this problem is probably a graph question. So knowing this, we're going to define our nodes and edges. And in this case, we're going to make our nodes our cities, and our edges are going to be the routes. So what this means is if I have the routes 1, 2, and 3, and then 3 and 2, we are able to create a fully connected graph for each route. So for 1, 2, and 3, notice that for this question, let's say the cost of this is 4 and the cost of this is 3. Notice that for this question, the cost of from 1 going to 2 is the exact same as the cost of 1 going to 3 if we're following this route. So what this means is we're going to have a fully connected graph here with the weights being 4 just to represent this one path. And to represent this path, what we're going to do is we're going to have another connected graph. So this is going to look like this with 3. So notice that in this case, since our edges are just going to be the routes, we can actually have two nodes that connect to each other in the same way with different weights. So if we had two different routes, this is fully possible. So the algorithm we're going to be using is actually going to be greedy and Dijkstra's. Since we're looking for the minimum amount, we're going to be using a greedy algorithm, and since this is a graph, that probably means it's Dijkstra's. So for the data structures of this question, there are three main ones we're going to go over. So the first one is the main implementation. It's going to be a distance matrix. If we were to store all of the routes, what actually ends up happening is we time out. So in this case, we are literally just going to store a matrix of all of the different points and their minimum distances. So if we had 1, 2, 3, 3, 2, and 4, 1, 2, with weights 2, 3, and 4 respectively, we are going to basically create a matrix that has the minimum distance of between these 2 points. So from 1 to 1, this distance is going to be 0 since it's 0. And actually we can initialize all of these to 0 since from one city to the same city is 0. We're going to start off by initializing the rest to infinity, and every time we have a path like this, we're basically going to find the minimum. So what this would look like for this specific example would be from 1 to 2 for the first path, we can put a 2 for now, since this was cost 2. From 1 to 3, we can also put a 2, and from 2 to 3, we can also put a 2. So from 2 going to 3 is going to be here. From 3 going to 2 is going to be this point. So over here we have one dimension, which is the first city or the starting city, and then the second dimension is going to be the city we reach. And so we're going to continue on with this example. We're going to have from 3 to 2, so starting from 3 and going to 2, this is 3, and then we're going to have from 4 to 1, and this is going to be 4, from 4 to 2, and this is going to be 4, from 1 to 2, so 1 to 2 is already 2, so we're going to compare the value of 2 to the cost of 4, and we're going to see since 2 is smaller, we're going to leave this here. And then the rest of these we actually can't reach, so we're just going to mark those as infinity. And then the second main data structure is just going to be visited. That's your typical visited of nodes. And then the final one is, because it's Dijkstra's, a priority queue. So in this Dijkstra's, the first thing we would think is, in our priority queue, we would need to store 3 things. We need to store our node, we need to store our weight or our cost, and we need to store the minimum amount of cities. So since this actually ends up being too expensive, what we're going to do is we are going to create a custom comparator with our priority queue. So we are going to have a separate vector of pairs, or a list of pairs, and we are basically going to store our node, and then using the custom comparator, we are going to compare with this vector. So I'll show you that in the code. So now we're going to move on to the coding part. The first thing we're going to do is we are going to put in our matrix and our data structures. So cost M is going to be our matrix. What it's basically going to store is, from one city to another, the minimum distance. We're also going to have a distances array. So what this is going to store is a pair of the distance from point A and the number of cities to take from point A. And then the final data structure we're going to have is going to be visited. And basically it's going to say whether or not we've already visited a city. So since we're using Dijkstra's, we're going to be using a priority queue. And for this priority queue, we're actually going to combine it with distances. And what we're going to do is we are going to have a priority queue of integers, which is going to store the city IDs. But we're going to have a custom comparator that's basically going to compare the distance from A. So we're actually going to store the distance of the city from A in here, and we're just going to use a custom comparator to get that value and then compare it. So this is going to return the city in the priority queue with the smallest distance from A. Okay, so now that we've done our data structures, we're going to move on to the actual program. So we're going to read an input, and we're going to basically set up the program. Okay, so now we're going to set up the program. The first thing I'm going to do is I'm going to set up my matrix. So I'm going to set everything to infinity, except for the values where it's from the same city. So what this means is traveling from city I to city I. So obviously the distance is just going to be 0 because there's no distance in between. And then the next thing we're going to do is we're actually going to read in the input. So over here, we're going to have our input. I'm going to read in 2 values, the cost and the number of cities, or the length of the route. And then we are going to have our route. We're going to read it in, and then what we're going to do is, for our distances matrix, we're going to basically update all of the values from earlier in the route into later in the route. So what this means is, if I have a route like 1, 2, 3, 4, I'm going to read in the value of 3, and then I'm going to update the cost, our matrix, for the distance between 1 and 3. I'm going to update this value to the minimum cost, and then I'm going to update the value of the distance between 2 and 3. So this is going to be 1, 2, and then we're going to move on and read in 3, and then 3 is going to find the distance between 1 and 3, 3 and 2, and then we're going to read in 4, and then it's going to find the distance between 4 and 1, 4 and 2, and 4 and 3. So this is just creating our matrix. Now that we've read an input, the next thing we can do is start the actual Dijkstra's part. So we are going to set up our distances, and we're going to push in A, our first city, into the priority queue. And then we are going to go into our while loop. So we have a Dijkstra's algorithm, and we're going to say, while the priority queue is not empty, we're going to read it in. We're going to set our value of cost and cities to the current city's cost and the number of cities it's taken. So the next thing we're going to do is we're going to check whether or not this is B. And so what this is going to do is we're going to basically check if our current city is B. And since this is Dijkstra's and a greedy algorithm, the first time we reach it, it's just going to be the answer. So if this current city is B, we're just going to return 0. And then the next thing we're going to do is we're going to implement visited. We're just going to say, if visited, we're going to continue, otherwise, no. And the final step of Dijkstra's is just to read in the children and push them in. So what we're actually going to do is we are going to go through, and we're going to go through all of the various values. So over here, it actually goes from 0 to maximum value. And what this means is we're just going to go through every single node, and we're just going to find the new cost and the new amount of cities. And this is going to be done by doing the cost, our current cost, plus the matrix's amount. And then the same thing for cities. And then, since this is Dijkstra's, we're going to implement a standard algorithm. Okay, so the next thing we're going to do is we're going to see whether or not we can... Okay, so the next thing we're going to do is we are basically going to check whether or not we can push our neighbor in. And the way we're going to do this is we are going to compare our new cost to our old cost. So in standard Dijkstra's, we have the new cost, and we basically see whether or not it is less than the old cost. If we were to do equal to in standard Dijkstra's, it would run forever. However, in this case, we actually have a second variable that the problem wants us to solve. So we also want to find the minimum amount of cities. So in this case, we're actually going to need to check the case where new cost is equal to our old cost. And we're going to, in this case, need to basically min our distances. So what this is going to do is it's basically going to set the value of distances dot second as the minimum amount of cities visited. And then we're just going to push it. Okay, and then the final thing we're going to need to do is we're basically going to say, if it never early exited here, it means we never reached B, so it's just going to be -1, -1, or not possible.